Hi guys, now that we've talked about intermolecular forces, it's time to talk about the properties that liquids have because of their intermolecular forces. First, we'll talk about the molecules in a liquid, and just a reminder that they have a definite volume, meaning they'll always have the same volume. That's what definite means, but an indefinite shape. So they'll take the shape of the bottom of the container that they're in. Kind of like a cat. Cats are like liquids. They take the shape of the container while maintaining a constant volume. Okay. Liquids have a relatively strong intermolecular forces. They're stronger than gases, but not as strong as solids, so that's why they're in the liquid form. They have things like hydrogen bonding, dipole-dipole forces, even some strong London dispersion forces. Liquids are fluids in that they are able to flow. So this water here, water is a fluid. It's able to flow, and you see it flowing down the river or stream or creek. Okay, next we need to learn the term viscosity. Viscosity is a substance resistance to flow. So how much it doesn't want to flow. It doesn't flow very nicely. If something is thick and gooey, like the purple substance in the upper right-hand corner of your screen, that has a high viscosity. It resists flow and it doesn't flow very nicely. It's kind of like getting ketchup out of a ketchup bottle. It's very hard to do that because ketchup has a pretty high viscosity. Something that has a low viscosity is something that's kind of thin as it pours out and runny. Okay, so there are two pictures down here, honey and water. Identify the one that has the highest viscosity. All right, so should have said that honey, okay, resists flow. It has a high viscosity. And then water, it's the opposite. It has a low viscosity. It's very thin and runny. All right, why do things have high viscosities? And that's because of their intermolecular forces. So the stronger the attractive forces are holding those molecules together, the more they're not going to want to move away from each other, and they're going to have a really high viscosity. They're just going to clump together. For example, motor oil. Motor oil, you see in the upper right-hand corner, is a long chain hydrocarbon. It's made up of a lot of carbons and hydrogens. And so since it has that long chain, there's lots of electrons within the carbon and the hydrogen atoms that can get pushed over to one side or the other, and you end up with those induced dipoles. Those temporary induced dipoles we call London dispersion forces, where part of that molecule will be positive, the other side will be negative, and so the motor oil will stick to each other. Here's just an animation of conventional motor oil versus synthetic motor oil. You can see that the conventional is pretty viscous, especially when it's used. It doesn't even want to come out of the container. All right. In terms of temperature, you've experienced this probably when making pancakes. If you've ever warmed up maple syrup, you've actually warmed it up and it comes out nice and thin and runny instead of thick and gooey. And so as you increase temperature, the viscosity decreases. And what's going on is that you're adding energy and you're making it easier for those molecules to pull apart from their intermolecular forces because they have the energy to do that. Okay, so you see that picture there at 0 degrees, whatever substance this is, it doesn't really move, but at 100 degrees, it pours out very nicely. All right, so I have a picture here for you. Which liquid has the strongest intermolecular forces? Let's see if you've got this. So there's A, B, and C. They're all three different substances, and you see a marble placed in. All right, so the strongest intermolecular forces are going to have the highest viscosity. They're going to resist flow. And so the one that is resisting the flow of the marble falling down is C. So hopefully you said C. Okay, we're going to talk about liquids being sticky. And they're not really all sticky. It's just those molecules stick together in the liquid form. All right, so first, liquids tend to have surface tension. And that is the inward pull of particles by the interior molecules. We'll talk about that. The stronger the intermolecular forces are, the higher the surface tension. So if we're looking at water, which can hydrogen bond, okay, water, let's say this is water right here. you've got all these particles pulling in each other, trying to hydrogen bond. Now they don't stay stuck, they continue to move and form new hydrogen bonds, but they're feeling the pull from all the molecules around them. Okay, so if I'm looking at A here, this molecule is feeling the pull from all of these. B is a little bit different in that it's on the surface. Okay, B is feeling the pull from these molecules here. And since there's nothing to counteract this pull, like A has these 3 molecules up here to pull upwards, this is feeling a net force downwards. Okay, so B feels a pull down. And what ends up happening is a bunch of the surface molecules feeling that pull downward come closer together. So the top part, you end up with a lot of molecules lined up right here, really close together, and it kind of forms what we call a skin on the surface, okay, which we call surface tension. Okay, the bug on the top corner of your screen is taking advantage of the surface tension of water. And see, he's floating on top of the water. If you've ever done a belly flop in a pool, you've also felt the surface tension of water. Another thing that uses surface tension to its advantage is what we call Jesus Christ lizard. I'd like you to watch to see why we call him the Jesus Christ lizard.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
Pretty cute. Next. Okay, so I missed that one. If you ever want to experience running on water, you can make a big giant pool of oobleck. Oobleck is cornstarch in water, and what happens with oobleck is that it acts kind of like in between a solid and a liquid. When it's not kind of disturbed, it's mostly acting like a liquid, and then as soon as you apply a force, it acts more like a solid. So as soon as it gets a lot of pressure, those molecules line up and you get a solid. And so this person is able to run on the oobleck. If she stopped, she would fall straight down. All right. Another vocabulary term that you need to know is a surfactant. And what a surfactant does is it breaks up hydrogen bonds and it lowers surface tension. And so kind of how soap works, in that the soap molecules have a hydrophobic end and a hydrophilic end, and one side attaches to the water, the hydrophilic end, and the other side attaches to the dirt or whatever oil there is. But by doing this, it breaks up the hydrogen bonds that are there. It kind of disrupts them from each other and breaks up their surface tension. All right, next we have cohesion, and cohesion is an intermolecular attraction for the molecules with the same substance. So basically, it's another word for saying it's intermolecular attractions, okay, for itself. Adhesion is the intermolecular attractions between that molecule and something else. And so you see this water droplet here on a leaf. The water droplet, the water attracted to the other molecules of water, that is cohesion. They're sticking together. And then adhesion would be the water molecule sitting on top of the leaf. The water is attracted to the leaf. Okay, because of cohesion and adhesion, we have capillary action. And that's just the ability of a liquid to go upwards in a small tube against the force of gravity. Okay, what happens is the water molecules being attracted to each other, okay, cohesion, and then adhesion, them attracted to the sides of the wall, allow it to climb. Now, adhesion has to be greater than cohesion, so the attraction for the walls of the container has to be greater so that you can end up with a net force upward. Now, the other thing about cohesion and adhesion is it gives us this meniscus in a graduated cylinder. And so whenever we say to read the graduated cylinder, we read the bottom of the meniscus. And the reason why we see it is because we see the molecules or the water molecules adhering to the graduated cylinder itself. Okay, so write that in. It creates the meniscus. All right, up in the upper right-hand corner, you have some flowers. Those have also taken advantage of capillary action in that the dye underneath them in the containers that they're in have been drawn up the stem and changed the color of the flower. So they didn't start out that way, they were actually dyed. Well, that's it for today. I hope you learned a little more about the intermolecular forces in liquids.